Alright, back with another familiar setup. Because the cylinders in example 8.4 are left rotating at angular velocities omega A and omega B, say, there's actually a residual magnetic field and hence angular momentum in the fields, even after the current in the solenoid has been extinguished. If the cylinders are heavy, this correction will be negligible, but it is interesting to do the problem without making that assumption. Alright? So, A, calculate in terms of omega A and omega B the final angular momentum in the fields, where we define omega is equal to omega z hat, so omega A and omega B could be positive or negative. B, as the cylinders begin to rotate, their changing magnetic fields induce an extra azimuthal electric field, which in turn will make an additional contribution to the torques. Find the resulting extra angular momentum and compare it with the results you found in A. Alright, let's go ahead and see what the diagram shows. Here again, we've seen the solenoid and cylinder setup, so I'm not going to spend too much time on it, but it's going back to this question. Alright, so for part A, the rotating shell at radius B produces a solenoidal magnetic field between A and B. So we see that B at B, the B field at radius B is equal to 𝜇0 hat, which again we saw was sigma B omega B radius B. So we just plug everything in that we need to for this. You see B's cancel once we plug in the surface charge for it. And we see that the B field is equal to negative 𝜇0 omega B Q over 2 pi L z hat direction. And we need to note that if the angular velocity is defined with respect to the z-axis, then omega B is a negative number. The shell at A also produces a magnetic field BA, which is equal to the opposite of this, with omega A in the region for S less than A. So the total field inside the inner shell is B on the inside is equal to BA plus B at B. So you take the minus of them and you see that we get 𝜇0 Q over 2 pi L omega A minus omega B for S less than A. Okay, so meanwhile, the electric field on the inside, well, this is just equal to 1 over 2 pi epsilon naught with lambda over S. Okay, Gauss's law, make that easy. But we know that lambda is equal to Q over the length L. And so we get L in there, and we see that we, for S in between A and B. So the momentum the momentum density in the region between A and B is, well, take the cross product to E and B, and we see that the epsilon cancels, go figure. We had a negative sign there out front from the B field. Again, we don't use the contribution of what's inside A for the B field. We're just using the contribution of B here since we're between A and B. So then once we factor out all the constants, what we see is that we have S cross Z with a negative, which allows us to switch the order of Z cross S. We do that again since we know that we want to take the cross product in cylindrical coordinates. So Z cross S gives us phi hat instead of having a negative phi hat. Just makes it easy for us. All right, so now to find angular momentum, we need to take R cross G, which we know that R cross phi hat will be we need to take that cross product, which we do in purple. R is equal to S hat plus Z hat, some point in space. And so if we take the cross product and distribute it with phi hat, of course, we get S cross phi, and then plus Z cross phi, which gives us this twisted notation almost. So we get S Z hat minus Z S hat. Kind of weird, but do take into account the signs. So, and S hat terms integrate to 0, so integrating with Z. For big L, we get 0 to L, 0 to 2 pi, A to B of this whole thing with d tau cylindrically. And we just split everything up, and we see we get a lot of cancellations from the integral, and you see we're left with the angular momentum of 𝜇0 omega B Q squared over 4 pi L with B squared minus A squared in the Z hat direction. Okay. So now for part B, the extra electric field induced by the changing magnetic field due to the rotating shells is given by, well, let's use Faraday's law. Take the closed integral of E dot dl and take the negative time derivative of phi, the magnetic flux, And we see that we get E is equal to negative 1 over 2 pi s d phi dt in the phi hat direction. So for a region in between A and B, the flux is from 0 to A and A to S. With that being said, we can split this up from the B field inside and the B field outside with the appropriate limits. And so we do that on the next page, and we see that we go from 0 to 2 pi and 0 to A with the Bn that we solved for in the first part of this question, and plus the B at B part, so from A to S. And yeah, just let the calculus work its way through. We see we get a lot of 2 pi's canceling from the phi integrals. We get A squared over 2 and S squared minus A squared over 2 from the second integral. Be very careful how we combine these things. After we simplify and factor out mu naught Q over 2L, we get omega A times A squared, and then we get a minus omega B A squared, and then minus omega B S squared plus omega B A squared. So omega B A squared cancel, and we're left with the mu naught Q over 2L, omega A squared minus omega B S squared. All right, so here then the E field is equal to negative 1 over 2 pi s mu naught Q over 2L, and then times the derivative, times A squared with the time derivative of omega A and omega B in the phi hat direction. Okay, so we need the torques in all the locations of the cylinder with S equal A and S equal B. Since the torque on the shell is N equals R cross F, which is equal to R cross EQ. Now we just need to see that RE clearly being in the phi hat direction and R being in the S hat direction. We need to simplify that through, which gives us Z hat. All right, so we're good to go there. And thus we see that for in A, the torque on A, if we go ahead and plug that through, we get a cancellation there of A's in the form. And we can go ahead and, cancel out the A's, Q squares, and we have that simplification to the right-hand side, factor the A's out. Good to go there. Similarly, in B, we're going to have to cancel the B's. We can't do any factoring since S goes to B there. And so to find, again, we're going to split this up so we get LA and LB momentums, and then we'll add them together. LA is equal to NA dt, LB is equal to NB dt. Run it through, you see the integrals there. The dt's cancel, and we're left with the change in omegas. So we get omega A minus omega B, good to go. Similarly, you get the change in omegas again. The dt's cancel, so they get let off. And if we add the two together in the z hat directions, we have to be careful on the factoring to simplify them. So we factor out a mu naught Q squared over 4 pi L, negative A squared times omega A minus omega B, plus A squared omega A minus B squared omega B. Clearly we see that an A omega A cancels, so we can simplify that even further, going back to mu naught QS over 4 pi L, A squared omega B minus B squared omega B. And so we're able to factor out the omega B, so we see that the L total is equal to mu naught Q squared omega B over 4 pi L, A squared minus B squared. And if we factor out a negative from both of those, we can have B squared minus A squared. And thus the reduction in the final mechanical angular momentum, B, is equal to the residual angular momentum in the fields. Holy cow, they are the same. That is freaking awesome. The field momentum is equal to the mechanical momentum. Everything stays conserved. This is a wonderful, wonderful conservation law.